Here's an introduction to the terrestrial planets to accompany Chapter 7 of the textbook Astronomy from Open Stax. So by terrestrial planets, I mean the terrestrial planets of our solar system, not in general. So we have Mercury, Venus, Earth, and Mars in the order that they are from the Sun. And here you can see their relative sizes all together and their colors. And usually when we discuss the terrestrial planets, which I'll go into in more detail, often the moons and other rocky objects are included in this, as well as the asteroid belt. So I'll touch on each of these, basically just giving a slide per. If you want to know a lot more about planets, that's what Astronomy 1001 is pretty much about. It focuses solely on the solar system and mostly on the planets and moons. So Mercury is the closest terrestrial planet to the Sun. For all the planets, I'll be showing the zodiac symbol, or really the astronomical symbol, because they all have them, which are kind of fun. But Mercury is very close to the Sun. It has an 88-day orbit. It's relatively eccentric, so you can compare the actual orbit to a circle. The eccentricity is 0.2, which in the wide world of ellipses isn't very eccentric, but for the solar system it's hugely eccentric. And it's there's a gravitational interaction between it and the Sun such that only 1.5 Mercury days happen per year. So it rotates 1.5 times each for each orbit cycle. It's really small, right? It's 0.06 Earth masses. That's quite tiny. And partly because it's so small, the geologic activity ceased a long time ago, so it was able to cool off, and that kind of initial heat just from it forming is pretty much gone. And there's no significant atmosphere because it's small. It just can't really keep hold of any kind of gas that's around it. The atmosphere is really just from energetic particles from the Sun, the solar wind kind of ablating the surface, and that generating kind of a dust atmosphere, and that gets lost pretty much. So there's always just a very thin atmosphere there. And because of that, there's a highly cratered surface. So since there's not really any geology going on the surface anymore, that can't erase craters the way they've been erased on the surface of the Earth. And there's not an atmosphere to blunt the impact of meteors because there's just no air there. So you have a very heavily cratered surface. And another interesting feature about Mercury, when you look at the surface, if you look carefully, you'll see there's these long kind of stretch marks, almost is what they look like, that go across the surface. These things are called scarps, or also called wrinkles. And what they indicate is that the interior cooled after the surface had already hardened into a crust, and so that caused these kind of compression wrinkles that stretch, large distances across the surface of the planet. Just kind of neat looking. So moving on to the next planet, Venus. This one has a 225-day orbit. The day is actually a little bit longer than the year, so it takes 244 Earth days for it to spin around, so very slowly rotating. And it's actually rotating in the opposite direction of the other terrestrial planets, albeit very slowly, but nonetheless in the opposite direction, which is kind of interesting. The atmosphere is extreme, so it's mostly carbon dioxide. The pressure is 92 times that of the surface of the pressure at sea level on the Earth. That's extremely high pressure. That's like going a kilometer under the sea, right? You'd need a submarine to do that. That's just the atmospheric pressure on the surface. The temperature is similarly extreme, 870 degrees Fahrenheit. That's extremely hot. The joke is that it's hotter than hell, because if you scour through the Bible, you'll find a reference to hell being hot enough to melt brimstone. And the melting point for brimstone, which is like a sulfur mineral, is something less than this. It's 740 some Fahrenheit or whatever. So in any case, 870 degrees Fahrenheit, just extremely hot, and it has clouds of sulfuric acid. So it's really just an awful place in terms of if you're thinking about from a life form's perspective. Partly because this atmosphere is so thick, basically, it's so dense, the temperature is nearly isothermal, meaning the temperature at one place or another is almost the same. So you can go from the equator to the pole, and the temperature is hardly any different, right? Which is markedly different than what we have on the Earth, where you're very cold at the poles and hot at the equator. Part of that is also because there's not a tilt to Venus relative to the to the sun, like we have on the Earth. There is significant volcanic activity. So there was actually one lander that was placed onto the surface of Venus, or they sent two landers, two separate landers, to the Venusian surface, and it's sort of a volcanic rock, right, coating a lot of the surface. And this thing, if I remember correctly, it lasted for like an hour or something like that, and then obviously it succumbs to the heat and pressure, which is very extreme. So really the surface of Venus is probably the most extreme place in the solar system, I would say. Moving on to Earth, you know a lot about the Earth, but here are just some statistics. So 10 to the 24 kilograms, about 6,400 kilometers in radius. And we know the most about this planet and the solar system for obvious reasons. And so one thing we can tell is that it's rather lumpy. So not just from looking at the surface, like mountains and such, but you can also measure the surface gravity. And from measuring the surface gravity, you can tell that underneath the surface of the Earth, there's also some lumpiness. It's not like a perfect ball. And here's, what the Earth looks like from the moon in the famous Earthrise picture. It is the most dense planet in the solar system. Mercury's pretty close, but otherwise Earth is it is the most dense. Again, we know a lot about it because we live here and we can do lots of scientific experiments. There is a rather large metallic core, so this is why it's a high density. So we're talking about iron and nickel. There's then a thick layer of pretty dense rock. This is what we call the mantle. And then you have this thinner layer of somewhat less dense rock that we call the crust. And of course, then that's coated with your ocean and your atmosphere, which from a thickness perspective are pretty negligible, but of course from our perspective are rather significant. In terms of how we know this about the inner structure of the Earth, we know something about the composition of the mantle because of volcanic activity, but mostly we know about this density structure because of seismic activity. So you can study how sound waves from earthquakes, for instance, and from man-made earthquakes, how they propagate through the Earth, and measuring those sound waves tells you about this density structure. The Earth is still a rather hot rock, which is good for us. Geothermal heat's a good thing. So a lot of this heat is left over from just the planet forming, so being a very hot molten object, and then it's still cooling off. And then a really large fraction is from radioactive decay. It's not exactly known what the exact breakdown is. It could be 50-50. It could be more radioactive heat than internal heat left over. But in any case, a significant amount of heat from both. And the main sources of radioactive heating are these four long-lived nuclei here that have extremely long lifetimes, and so they undergo radioactive decay, and that releases heat then into the part of the Earth where these are located. The moon, all natural satellites of planets are called moons, but ours is just the moon. Sometimes people call it Luna to distinguish it from other moons. It's only 1% of the Earth's mass and 1/3 of its radius. It's heavily cratered, right, looking at it. And it's, relatively speaking, it's pretty close to the Earth in terms of the Earth to Sun distance. However, if you look at the relative sizes down at the bottom here, here's the Earth and here's the moon. And so the scale here is accurate. And so you can see it's still pretty far away. Um, the density itself is about 2/3 the density of Earth, and that's because it's mostly rock. So remember, the Earth has a large metallic core. There's a very small metallic core to the Moon, but nonetheless, it's the second most dense moon in the solar system. It has one rotation per each orbit, so that's why when you look up in the night sky or even in the daytime sky and see the moon, you always see the same face because it's rotating at the same rate that it's orbiting. And this is due to a gravitational interaction called tidal locking, similar in spirit to the tidal locking that we talked about for Mercury's orbit and rotation. The craters are impacts from space rocks, right? So from, for instance, stray asteroids blasting into the surface, or chunks of asteroids blasting into the surface. And so, what happens is your rock comes in, it impacts, in this case, the moon. What winds up happening is it digs out a crater that is many times larger than the size of the actual rock itself. And because it's excavating material here, you get material heaped up along the surface of the crater. So the craters aren't just divots, but rather they're like there's a cusp and then a bowl, and that's because the excavated material has to go somewhere, and naturally it's mostly going to land close to the rim here. Interestingly, if you want a close analogy on Earth, so we obviously have crater impacts, but one way you can study impacts like this is with explosions. So there's so much energy being brought in and so much energy dissipated that this is very comparable to exploding a bomb. And so you can create crater-like features by exploding a bomb on Earth, for instance. The stuff flung from the craters creates these crater rays. So, for instance, you see this crater here is named for Giordano Bruno, guy who was burned at the stake for suggesting that there are other planetary systems out there. And you see, if you look closely, there are these rays of material propagating from there. And under the proper light, if you look at the moon, you can actually see it with a small telescope, or maybe even with your naked eye if you have really good eyes. But there are these rays that go from there, and these are basically just dust blasted from the crater itself. And it's no surprise that the moon is one of the moons that we know the most about, because we've been there, collected rocks, and also there are seismic probes on there, so that's how we can study the internal structure. Mars is the last terrestrial planet, so it's about 1.5 Earth to Sun distances from the Sun. It takes around 2 Earth years to go around the Sun, and the day's pretty close to the length of the day on Earth. So right, it's about an extra 40 minutes or so. The surface is covered in a thin layer of dust of iron oxide, and that gives it this red tinge, which is why we call it the red planet. The atmosphere is extremely thin, so it's less than 1% of the Earth's atmospheric pressure, and mostly comprised of carbon dioxide. It is extremely dusty, and dusty to the point that when you observe it, when there's not a dust storm versus when there has been a dust storm, it's very obvious, right? There's a huge qualitative difference between these two, just because there's so much dust available on the surface of the planet. Part of this is that there's no ocean and no humidity to absorb that dust, so it just kind of stays around on the surface, and there's weather on Mars, and that can cause dust storms and even dust devils, and when you have large dust storms, you get that kind of milky appearance to it. So it's long been speculated, and somewhat recently was measured, that there are Mars quakes. So this is seismic activity like you have on the Earth and you have on the Moon. And it's really exciting that we see these at all. And what's more exciting is with future space missions, we'll likely be able to use Mars quakes to learn more about the internal structure of Mars, as we have done on the Earth, because you can use the way that sound waves reflect within the planet to learn about the density structure, which is pretty neat. And Mars is the only other terrestrial planet besides the Earth that has any moons. It has 2 moons, but they're really small, right? Phobos and Deimos are tens of kilometers, and they're pretty oblong shaped. It's not clear how they came to be moons of Mars. A favored scenario is that they're captured asteroids because they kind of look like that, and it's thought that the composition is a bit different than Mars, so that would support that. But ultimately, we don't know. That's just the best. Most of the evidence at the moment supports captured asteroids, but that may change. And then to round things out, just beyond Mars, in between Mars and Jupiter, we have the asteroid belt. And because these are rocky objects, they're generally lumped in with our terrestrial planets. So you have 10 to the 21 kilograms of mass, and this is distributed amongst a whole bunch of rocks. So we don't really know how many asteroids are in the asteroid belt because it depends on what your size cutoff is. If you restrict it to kilometer-sized object, we think that there are millions. If you go down to several meter-sized object, then there are hundreds of trillions. So whatever, it's a whole lot of rock. Now most of the mass is though concentrated in just a few large objects. So for instance, there's the dwarf planet Ceres has most has a plurality of the mass of the asteroid belt, and partly because of that, it gets its own astronomical symbol. It is the only one that's considered a dwarf planet because it is spherical and it is in a hydrostatic equilibrium where the pressure is balancing the gravity. There are a few more relatively large objects, but they're not spherical. So one example here is Vesta. It's also called 4 Vesta. It's about half the radius and it's not large enough to be spherical, but it does get its own pretty neat astronomical symbol. In movies, you'll see that the asteroid belt is this maze of rocks that you have to fly your spaceship around in. That's not what it's like at all. Maybe that's a little disappointing. It's certainly convenient when we send space probes out to distant planets. The asteroids aren't anywhere near each other. If you just calculate the volume that the asteroid belt takes up and then have the number of rocks, you have a huge amount of volume per every asteroid. So the collisions are pretty rare in terms of day-to-day life. In terms of astronomical timescales, collisions between big asteroids, big being like kilometer size or so, these will happen on the order of every millions of years. So astronomically speaking, it's pretty frequent, and it plays an important role in the history of the solar system. But for day-to-day activity, the collisions almost never happen. What's interesting is that when you look at the belt, it's not as if there is a uniform belt of material. There are definitely distinct clusters. And this will play into we'll talk about this in next week's lectures when we talk about the origin of the solar system. This provides a clue as to how the asteroid belt formed. When you look at the asteroids, for instance, we can have a histogram, so just the count of the number of asteroids per distance from the sun. And the units here are Earth to Sun distances, astronomical units. You see you have distinct clumps here, so there are some gaps between these. This gives you some clue as to how the asteroid belt formed. And similarly, you can plot the asteroids as a function of the inclination angle, so how high this thing is, how tilted it is with respect to the ecliptic, versus the eccentricity of the orbit, so how non-circular is the orbit, and you have very clear blobs that jump out at you. So there are definitely more dense and less dense regions, and as I mentioned, this is going to tell us something about how this formed. And that is it for this introduction to the terrestrial planets for Astronomy 1000.